Hi everyone, welcome back to my channel. In the last few videos, we have been discussing about applications of Coulomb's law. In today's video, we'll discuss about continuous charge distributions. Before that, if you are new to my channel, please do subscribe. We know that charge can exist only as an integral multiple of basic charge E. Therefore, we can say that charge distribution is always discrete. But this is applicable only in the microscopic level. When we go on to the macroscopic level, this is impractical because we cannot specify the charge distribution in terms of location of each and every electron. Let us consider a small area on the surface of a spherical conductor. So this area may be called as delta S, and this area may be small in the macroscopic level, but in the microscopic level, this area is huge enough to contain lot of electrons. Let the total charge in that small area delta S be delta Q. Then we can define a quantity called charge density. Charge density sigma can be written as delta Q divided by delta S. Here sigma is a surface charge density. We can compare this to the density of a liquid. When we refer to a density of a liquid, we are referring to its macroscopic density. We are treating it as a continuous fluid and we ignore the molecular level discreteness that is having. So basically there are three types of charge densities: linear charge density, surface charge density and volume charge density. If a charge is distributed along a straight line, then we can find out linear charge density. Let us take an elementary length delta L, then that elementary length will be having a charge delta Q. Then we can define the linear charge density lambda equal to delta Q divided by delta L. So if you want to find out the total charge of that distribution, we can integrate, that is integral delta Q equal to integral lambda dl. If lambda is a uniform charge density, we can take that lambda out of the integral. Now let us move on to surface charge density. When charge is distributed on the surface of a conductor, we can consider a small elemental area delta S, and that area will be having a small charge delta Q. Then we can define surface charge density sigma equal to delta Q divided by delta S. Now if we want to find out the total charge on that conductor on the surface, we can find integral delta Q equals integral sigma into ds. Now let us move on to volume charge density. When charge is distributed along throughout the volume of a conductor, we can take a small elementary volume delta V, which will be having its charge delta Q. Then we can define volume charge density rho equals delta Q divided by delta V, and the total charge in that volume can be written as integral delta Q equals integral rho dV.